Hi, welcome to this video in which we'll be covering past paper questions for mechanics for CSEC physics. From January 2010, complete the following table by inserting the correct quantity, formula and unit for 3 marks. We're given the formula F is equal to ma, and we know from Newton's second law that is force is equal to mass times acceleration. So the quantity is force, and the unit is newtons. The SI base unit equivalent, when you multiply mass in kilograms times acceleration in meters per second squared, is kilogram meters per second squared. For the quantity potential energy, the formula is mgh, mass times gravity times height. Energy is measured in joules, and the equivalent SI base unit is kilogram meters squared per second squared. Alternatively, potential energy can be measured in Newton meters. In the last row, we're given the unit kilogram meters per second. This is the unit of momentum, which is calculated by multiplying mass and velocity. And just like that, 3 marks. Next, we're asked to state the law of conservation of linear momentum. This law states that for two bodies undergoing collision, the total momentum before the collision is equal to the total momentum after the collision, if no external force is acting on the system. The stimulus: big crash on the highway. Two trucks of equal mass collided head-on at the same speed on the busy east-west highway. They both remained stationary on impact. We're asked to explain this crash in terms of conservation of linear momentum. Assume the masses of other contents of the trucks are equal. Now, we're given in the information that two trucks collide, and importantly, they are of equal mass. They collide head-on at the same speed and remain stationary on impact. Now, we just stated the law of conservation of linear momentum, so we know that the total momentum before the two trucks collided must be equal to the total momentum after the two trucks collided. We know that momentum is equal to mass times velocity. And if the trucks were of equal mass colliding at the same speed, that must mean that the absolute value of their momentum is the same. And I say absolute value because the trucks collide head on. So when you have one truck colliding with another, one has a positive velocity and one has a negative velocity, because velocity is a vector. Therefore, we know that the total momentum before the collision is going to be 0. Positive of one value plus the negative of the same value gives you 0. Right. The next question. A police recruit, while training, shot at a stationary target of mass 5.0 kilograms with a bullet of mass 0.1 kilogram. The target was mounted on low friction wheels, and as soon as the bullet struck the target with the embedded bullet sped off with a velocity of 6.0 meters per second. Calculate the velocity of the bullet just before it hit the stationary target. By the law of conservation of linear momentum, the initial momentum is going to be equal to the final momentum. We have the bullet and we have the target. We're told that the target has a mass of 5 kilograms and is stationary, and that the bullet is fired at a velocity we need to calculate. So, the mass of the bullet times the velocity of the bullet plus the mass of the target times the velocity of the target is going to be equal to the mass of the bullet and the target, since the bullet is embedded in the target, times the final velocity. We're given that the mass of the bullet is 0.1 kilograms, the velocity of the bullet is unknown, the mass of the target is 5 kilograms, and the velocity of the target is 0. The combined mass of the bullet and the target is going to be 0.1 plus 5.0 times 6 meters per second. Therefore, 0.1 times the velocity of the bullet is equal to 5.1 times 6. The velocity of the bullet is equal to 30.6 over 0.1, which gives us a value of 306, and the unit of velocity is meters per second. Since momentum is a vector, it would be useful to put that velocity is in the direction of the target, so moving towards it. And that's our question. Next, from January 2012, complete Table 2 by relating fundamental quantities and their base unit symbols. We're given that the symbol of mass is m and the SI base unit is kilograms. The symbol for time is a lowercase t, and its base SI unit is seconds. Current, capital I, base unit, amperes. Temperature, capital T, base unit, Kelvin, not degrees Celsius. Length, lowercase l, and base unit, meters. State the difference between a linear scale and a nonlinear scale. Now, a linear scale has equal spacing between values, while a nonlinear scale has unequal. Now, a linear scale has equal spacing between values, while a nonlinear scale has unequal spacing. Next, you are provided with the following 3 measuring instruments: meter rule, clinical thermometer, and conical flask. Which of the instruments listed above has a nonlinear scale? And we can see that the one which has unequal spacing between intervals is the conical flask. The next question: the container shown in figure 2 is completely filled with cement. If the mass of the cement is 15,000 kilograms, calculate the density of the cement sample in kilogram per meter cubed. Now, we know that density is equal to mass over volume. We know that the mass of the cement is 15,000 kilograms, and the volume must be the product of each of its sides. Since here, volume is equal to length times base times height. Putting this into our calculator, we get 2,727.273. The two significant figures, this is 2,700 kilograms per meter cubed. What pressure would the cement exert on the base of the container? We need to know the base of the container, which you can see is 1.1 times 2. Therefore, since pressure is equal to force over area, where area is the base of the container, that is going to be equal to the mass times acceleration due to gravity over the base dimensions, which gives us 68,181 newtons per meter squared. To two significant figures, 68,000 newtons per meter squared, or 68,000 pascals. From January 2014, Figure 1 shows some physical quantities and their units. Draw an arrow from each quantity to its unit. Starting from the top and going clockwise, the meter is the unit for displacement, so we draw our line from displacement to meter, not the other way around, because it has to draw it from each quantity to its unit. Unit of force is the newton, and of moment is the newton meter. Next, complete Table 2 to show the names of 3 forces and a situation in which each force acts. Here we have a javelin falling in the air. Firstly, it has gravitational force, weight, acting on it, as well as air resistance, so either works. For upthrust, you can think of submerging an object in water or in any other liquid at that. So I'll put a beach ball immersed in water. And we're allowed to choose our own force and situation for the third. There are many options to choose from. I'll use friction. Moving on. Patrick and Patricia showed their class a magical balancing act. They both sat on one side of a uniform 6.0 meter plank. Patrick sat 1.0 meters from the pivot located 0.5 meters from the center of the plank. Patricia sat at 0.5 meters from the pivot, on the same side as Patrick. Figure 2 shows the magical balancing act. X represents the pivot point. Label as W the point on Figure 2 where the weight of the plank acts. Since the plank is uniform, the weight of the plank acts in the center. Calculate the weight of the plank, W. Now we're going to use the principle of moments here. Which states that the sum of clockwise moments about a pivot is equal to the sum of anti-clockwise moments about the same pivot. Looking at our diagram, we have W as a clockwise moment, and Patrick and Patricia's weights as the anti-clockwise moments. Therefore, W times 0.5 is equal to 400 times 0.5 plus 500 times 1. 0.5 W is equal to 700. W is equal to 700 over 0.5, which is equal to 1400 newtons. If Patrick sat alone on the plank, calculate where he would have to sit in order to maintain his magical balancing act. The pivot remains the same as before. So Patrick's weight is constant. It's always going to be 500 newtons. Therefore, we need to calculate where he needs to sit without Patricia. We know that it is still true that the sum of the anti-clockwise moments has to equal to the sum of the clockwise moments. So therefore, if we take our moments about x, Patrick of weight 500 newtons has to sit at some position from the pivot, let's call that D, and that has to be equal to the anti-clockwise moment, the weight times 0.5 meters which it acts from the pivot. Therefore, D is equal to 700 over 500. 1.4 meters to the left of the pivot. From May-June 2014, the unit of energy, the joule, has two equivalent derived units. In Figure 1, indicate inside the bubbles the two equivalent derived units for the joule. The two equivalent derived units for the joule are Newton meter and kilogram meters squared per second squared. Solar energy is one of the popular alternative sources of energy. State one application of solar energy. There are a variety here. We can say powering homes, used in satellites or in calculators. I have my calculator on my desk right before me, so I'll say powering calculators. State one advantage of using solar energy in the Caribbean. Now, the Caribbean generally has year-round sunlight, which of course is needed for solar energy. So, there we go. A variety of alternative energy technologies are being used in the Caribbean and globally. Other than solar energy, complete Table 3 to show 3 other types of alternative energy technologies and their sources. So apart from solar, we have wind energy, which of course we get from the wind. We have hydroelectricity from flowing bodies of water. And finally, I'll put geothermal, which we get from heat in the center of the earth. Moving along, a basketball of mass 0.44 kilograms was dropped vertically from rest at A, 12 meters from the ground as seen in figure 2. Given that acceleration due to gravity is equal to 9.8 meters per second squared, calculate the A. Gravitational potential energy of the ball at the point of release, A, which we know is going to be the mass times gravity times height. We're told the ball is of mass 0.44 kilograms, that acceleration due to gravity is 9.8 meters per second squared, and that it is at a height of 12 meters. This gives us gravitational potential energy of 51.744 kilogram meters squared per second squared. Or 52 joules to 2 sig figs. Calculate the final velocity of the ball on reaching the ground 1.56 seconds later, assuming there is no loss of energy as the ball falls. Now, if we're assuming no loss of energy occurs, then that means that the kinetic energy it gains is equal to the potential energy it loses. Therefore, the kinetic energy is equal to the same value we obtained earlier. And just to be precise, we'll use the exact value. We also know that the formula for kinetic energy is half mv squared. We can use this to transpose the velocity. Velocity is equal to 2 times the kinetic energy over the mass, all square rooted. Two times 51.744 over 0.44, all square rooted. This gives us 15.336 meters per second. To two significant figures, 15 meters per second. Finally, calculate the ball's momentum when it hits the ground. Momentum is equal to mass times velocity. Its mass is 0.44 kilograms. Again, we use a precise value for velocity, approximately 15.34. Which gives us 6.7496 kilogram meters per second. To two significant figures, 6.7 kilogram meters per second. That concludes this video on mechanics past paper questions. All the best!